plus 4,320 newtons per coulomb. J hat. And so the sum, just add like terms. So 0.65, 1, 3, 5, 5. They're doing the fancy math here. 4, 3, 20, 2, 6, 5, 1.65. 5, 3, 8, 6. There's the electric field. Oh, let's put it in polar form. What the heck? Let's just do it. Just build on the excitement I'm feeling right now. How do we put this in polar form? And remember, this is your chance to show off for the international audiences from the throngs of people. Throngs of person who's going to watch this who's not actually part of the class.
Find the hypotenuse.
Yeah. All right, so I'm going to the left, 5,531.65, and I'm going down 1,668.35. Oh, no, sorry, wrong way. Up 1,668.35. The Pythagorean theorem, and what do we get as the hypotenuse?
I got 577.76.
577.76.
3 sevens.
777.76.
Yep, newtons per coulomb.
All right, so we got half of the answer, because again, there's a direction we have to consider. And let's go ahead and do that angle right there, and then we'll figure out what the complement is. Supplement is. So how would you find this angle? I would cleverly call it theta.
It's going to be arctan of
Yeah.
that number.
So theta is the arctan of, can you see this, Sarah?
I can.
Okay, well enough then. 1668.35 over 5531.65. And we get theta is, 22 degrees. 22.578.
$16.78.
Hey, I got a 7 and 8 there. Practically spot on. All right, so that is my angle theta there. So if I express the total electric field in, we'll just squeeze it in right here. My electric field, we have a magnitude of 5,777, so 5,777.76 newtons per coulomb, and my angle is
163.21 degrees.
Thank you. There we go. The 16.78 degrees is the base angle, but the actual angle in terms of indicating that's the second quadrant is the 163.21. Just in case you can't quite see that. I don't know, did pushing the board over do anything?
I can, yeah, I can still see.
You can still see.
Yeah.
So, on that lab, I mean, these distances, you would, well, you know the tick marks, and it's 5 tick marks is 2 inches. And then do a conversion into centimeters. Occasionally, someone can measure carefully enough and get enough decimal places for just straight measurement, but usually it's more exact to do the, you know, find the distance in tick marks and then convert. All right, any questions on this? All right, any questions?
Could we go through a capacitance problem?
Which type? The construct a capacitance or construct a circuit with capacitors in it?
With capacitors in it.
The one, okay, so I give you like 5 different capacitors and you come up with a configuration which gives a total capacitance within a certain range.
Oh wait, no, let's do the other one.
The other one where I tell you the size of the plates and the distance between them?
Yeah.
Okay. So if I have a capacitor hooked up to a battery, and then I mess around with a bunch of stuff with the capacitor, keeping it connected to the battery, what is gonna stay the same the entire time? If it's hooked up to a battery, what is gonna always stay the same?
The charge.
Not if it's hooked up to the battery. If it's disconnected, the charge. If it stays connected to the battery, what stays the same?
Voltage.
Yes. So let's start out with the capacitor. Let's assume that the size of the plates, well, actually, let's give you the size of the plates. Let's go for 0.7 meters by 0.7 meters. Let's keep them square. We'll make that the positive plate and the negative plate. Let's hook it up to a, say, 12-volt battery. And let's start out with no dielectric in between. And let's make this gap here 0.7, no, 0.2 centimeters. Or 0.002 meters. Wanted to make sure that this gap was less than 10% of each dimension of the plate, just so that we don't have to worry about exit. So we can use the approximation that these are infinite plates relative to the gap. Is that enough? Well, if it's not, we'll add something else in. So let's start out with, well, we got the basic quantities here. See, there's capacitance, there's voltage, there is electric field from the plates, there's the total electric field, there's charge. Those are the 5 main ones. Let's just throw in surface charge density. And our formulas. I know that for a parallel plate capacitor, that capacitance is equal to, well, equal to Q over delta V. Actually, that's true for any capacitor. For parallel plate capacitor, which is what this is, it is kappa epsilon naught A over D. I feel like I'm missing a letter there. We know that the total electric field is the electric field from the plates minus the electric field from the dielectric. Well, I'll go ahead and say plus. There'll be an opposite direction, so from a math point of view, you will subtract or add a negative, which is equal to, well, we'll leave it at that for the moment. I know that my electric field from the plates, and we'll just do magnitude, is equal to sigma over epsilon naught. The total electric field, magnitude, is sigma over epsilon, where epsilon is kappa times epsilon sub naught. And the total electric field is also equal to the voltage divided by the distance. Usually written as in the voltage is equal to A. And now it's just a matter of playing around. Okay, so let's start out with what I will consider the easiest one. What's the voltage between the two plates?
12.
Yes. See how simple this stuff is? In the middle of the test, you just shout out the question and someone will answer. Please don't. All right, so we got that one done. Do I have enough information to just start at the top? I don't know Q and C, so that equation is not really going to help us yet. There's no dielectric, so I know kappa, epsilon's a constant. I can find A and D, so I can use this equation to find capacitance. So 1 times 8.85 times 10 to the negative 12 times my area, which is 0.49, divided by the distance, which is 0.002. What do we get? This is around 2.5 times 10 to the negative 9. No, I'm off by exactly
2.17 times 10 to the negative 9.
Oh, okay. Units?
Farads.
Okay. Named after?
Farad?
Nope, it's one of the few that's actually not the guy's name exactly. Volt is another one not named after the guy exactly. Faraday. All right. So we now have capacitance. Go back to the top. I know capacitance, I know voltage, I can find charge now, because I have only one unknown there. So what is the charge on the plates? Or how would you find it?
You're gonna multiply capacitance by voltage.
Yep. And what do you get?
2.6 times 10 to the negative 8.
Units? Yes. He didn't sound confident though. All right, so first equation, we got all three of those. Second one, we're good with. Next one, for the most part, we'd only use if I said, hey, what's the electric field of the dielectric? But let's go to the next one. I know epsilons have not, got that one down. Sigma. Sigma is simple enough. Oh, I didn't write that equation down. What is the formula for sigma? Surface charge density,
So Q over A?
like you mean it.
Q over A.
There we go. I know the charge now, so this I should be able to do. So this is 2.6 times 10 to the negative 8 coulombs divided by my area of 0.49 square meters. So it's about 1.3, 1.2 something, 1.28. Oh, no, wrong way, oh, wrong way. Somewhere around 5.2.
I got 5.3 times 10 to the negative 8.
They're the same thing.
All right, units?
Does coulombs per meter squared have its own unit, or is it just coulombs?
That's just coulombs per square meter. And if you couldn't think of it, you could just go with, well, it's coulombs over square meter, so it's right there. And again, as one student would have written, coulombs per square meter times radians. All right, so we now have sigma, so we can find the electric field from the plates because we know the charge on the plates. So because we know the surface charge density, because we knew the charge on the plates, and we know what epsilons have not. So the electric field from the plates is sigma 5.3 times 10 to the negative 8 coulombs per square meter divided by 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. All right, so that's 10 to the fourth, something times 10 to the third, 5, 8, so somewhere around 6 times 10 to the third. Got something more precise?
5,988.7.
Let's finish it off.
Maybe it's pretty cool.
All right. What's my total electric field?
Same as the plates.
Why?
There's no dielectric in between them.
Exactly. And so we could actually throw in the other one here, the electric field, the magnitude of the electric field from the dielectric would be 0.
Just so I can
Sarah.
make the connection between our master set chapter 19, for this one it asks for the electric field between the plates and the electric field between the plates because of the plates. So which one matches
The electric
up?
field between the plates is the total.
The total. Okay, and then between the plates because of the plates is the plates.
Yes.
Okay.
Yes. Because we got two, if there's a dielectric, we got two electric fields competing with each other.
Between the plates because of the plates is the total?
Say it again?
Between the plates because of the plates is the total?
No, between the plates because of the plates is just based upon the sigma over epsilon, so not, the total would be sigma over epsilon. Brings the dielectric into it. Now, there's one equation that we have not used here, well, there's a whole slew of them, but the one equation that's written on the board here we have not used, we have not done that the total electric field is equal to the delta V over D. We can use this just to check ourselves. So if I do delta V, so this should also be equal to 12 volts divided by 0.002. Which is 6,000 volts per meter or newtons per coulomb. And so we can see there's a rounding difference in there. If it had not come out, then one of two possibilities. One, I gave too much information, which I have done before. Or two, you've made a mistake somewhere. Somebody made a mistake. It's a lot of fun as a grader when I realize I gave too much information, because now there are so many different paths to get an answer that it basically triples the amount of time it takes me to grade that problem. That's my punishment. And I will also say from a grading point of view, because at the end, there are two different ways of finding my total electric field here. If you had made a mistake with the voltage here, then that would have, potentially messed you up. And if I'm not seeing your work, then you are just trusting I can somehow figure out what you did. So please, the moral of the story, please show your work neatly, or as neatly as you can. If you scribbled all over a piece of paper, still handing that in is better than not, because there might be some chance I can figure out what you did.